Good evening, everyone. So there's some questions, mostly they are on pattern of the examination and all that. Let's not worry too much about that. We'll concentrate on the concepts and the basics. So some of them are, I'm leaving this question like how will be the exams conducted. So the exams will be conducted by NPTEL office, and it will be subjective. It will be like just like the questions that you had during your assignment session. It will be similar to that. Good evening. And of course, the answers to the questions will be given to you by the TA of the course, and she will post the solutions. We are trying to have it up to date. One important question from Aparna is that what is a pseudo gap? That's an interesting question. So first of all, let us understand what is a gap and how does a gap arise in a superconductor. So a gap arises in a superconductor because the Cooper pairs are formed, and there is a finite amount of energy required to break those Cooper pairs. So when you have a gap in the energy spectrum, this gap is coming because of the reason that you have a certain finite amount of energy required to break the pair and go into the normal state. In the BCS theory or in the conventional superconductors, all these pairs that are formed, they have both amplitude and phase coherence. Amplitude means they have the same, the magnitude is of a gap is the same for all of them. There is no distribution of gap, and each pair is has a phase which has a relationship with the phase of another pair. So there is so these are called coherent pairs. Okay, so every question, every sort of pair has a fixed relationship of its phase with another pair, and this is what we understand by pair. Now, pseudo gap is a phase where there could be amplitude coherence, but there is no phase coherence. That is, the phases are random, and there is no relationship between the phases. And as you know, could I have this board? So yeah, so the phase, let's write it with the black. So the gap has a form which is like this. So where delta 0 is the amplitude of the gap, and this theta is the phase. So each of the Cooper pairs, which are formed of a plus k up and a minus k down, this pair has the same delta naught, but the phase and the phases, sorry, not but. And the phases have a fixed relationship. Pseudo gap phase, the pairs have amplitude coherence but no phase coherence. That is, there's no relationship, fixed relationship. So basically this refer to the pairs formed in the normal phase. Okay, so this is pretty much what is meant by pseudo gap. Yes, I'm coming to this questions, the rest of the questions. I've already answered most of it. Some of these topics are a little advanced because superconductivity is a slightly difficult topic. It's the first topic in interacting electron theory, which you learn in your solid state physics, and this is slightly advanced topic. CDW ordering, somebody has asked, Chandan Patra has asked that about the CDW ordering charge density wave. Charge density wave and superconductivity can compete in some materials. We are not getting into the details of that. Charge density wave is a density ordered phase. At this moment, we are not talking about, we are just talking about a BCS phase and not considering a CDW, a competition between a CDW and superconductivity. But yes, there are some materials where such a thing can happen. Yes, let me see the questions. Ayan Kayal asked what are Cooper pairs. So the Cooper pairs are formed by when the the electrons basically, they attractively interact with each other and form a bound pair. So this is they can actually two electrons even being same charge, that is negatively charged, they should repel each other. But under the influence of phonons or mediated by phonons, they can attractively interact under certain conditions at low temperature and various things that we have discussed during the course. So these are called as Cooper pairs. Okay, so Cooper, Leo Cooper was a PhD student whose first PhD problem was actually forming a bound state of two electrons. And he showed that in presence of a filled Fermi sea, two electrons can form a bound pair even in presence of a very weak, infinitesimally weak attractive interaction. And this attractive interaction or potential rather. So this potential, attractive potential, is mediated via phonons. Yes. So now again, there was a question from Vaishnavi on Cooper pairs. So is this clear that two electrons forming a pair is known as a Cooper pair? Cooper because Cooper Leo Cooper invented it, or rather he first proposed that can happen. And this causes, so all these electrons, suppose you have n electrons in the problem, and there n by 2 pairs form, and this n by 2 pairs, they form and they go into condense into a ground state, and this ground state offers no resistance to passage of a supercurrent. This is the precisely, so just like your free electron picture, where you have all free electrons, possibly below the Fermi energy. Here we have all Cooper pairs. When they form pairs, they become free, and free means they are non-interacting, and that's why they are, allow passage of supercurrent through the through the material. So this is mainly the concept of Cooper pairs and so on. Well, density of states, and it is the most simple question in solid state physics. The density of states has to depend upon the dimension of space. Can I have this? Let me show you. It's probably there. Okay, so let us, understand it in this particular way, that we are talking about K space, right? Momentum space, which you know that it's the Fourier transform of the real space. So in the real space, we talk about a length scale as L. In the momentum space, we talk about the length scale, or rather the equivalence of that in the momentum space as 2 pi over L and so on. So in one dimension, if you so you have in the K space, you have all these points which are 2 pi L apart. Okay, where L is the, say, the lattice spacing or something like that. So this 2 pi L, if you walk in the K space, you have 1 K point. If you walk unit distance, you have L over 2 pi K points. And if you walk, so in one dimension, so if you walk a distance, say dk, that is, you want to know how many states are there between k and k plus dk. Then if you walk this distance, then you will get this many number of k points. Okay. Now, exactly the same thing, if you do it in 3 dimension, you will have to cube all these things. Okay. So you say that 1 k point and 1 this distance, you'll have this and so on. And then now you ask the question that what is the number of k points between a sphere of radius k and k plus dk. So in 3D, so it's sphere of radius k and k plus dk. So that available space is 4 pi k squared dk. So I need to ask the question, if I am there within a 4 pi, sorry, this probably doesn't, okay. So it's 4 pi k square dk is already there, okay. So, so it's 4 pi k square dk will have a 4 pi k square here. Now, you see that, now of course this is like a cube of that. And now, suppose you have a relationship between E and K, which is like K square. Okay, h cross square k square over 2m. All right. So then, so this is a non-relativistic relationship which can exist and so on. So you see that now this will go as a V. L cube is like V volume. Then it's a 2 pi whole cube, and then it's a 4 pi. And so if I take a dE, then it goes as 2k h cross square over 2m. So this 2 will cancel. So this will be like, so d epsilon will go like k dk, but you have a k square here. So you will have some power of this. So the density of states, which is the counting of state, number of states between k and k plus dk, is epsilon to the power half here. So this is in 3D, epsilon to the power 0 in 2D, and epsilon to the power minus half in 1D. So you see that as you go down in dimensionality, this from being, epsilon to the power half to epsilon to the power 0 to epsilon to the power minus half. So there's a strong, dependence on the dimensionality, and this is why solid state physics becomes different as you go from, macroscopic to nanoscopic, and that's why, probably the nano becomes so important, because you're going down and you are confining things in one dimension or in zero dimension, as it's called in quantum dots. You can tune this density of states, and because the density of states appear in all physical calculation of all physical quantities such as specific heat, susceptibility, magnetization, and so on. That's why you go from one dimension to another, and you'll have these results to be different. I have this. Okay, so next question, what is a Feynman diagram, as I see? So, and I guess you are, satisfied and convinced with the, the answer that I gave to your density of states question. Sudhanshu Nayak, Feynman diagram they have been, again invented by Feynman to explain the scattering processes. So when you have two particles scattering via potential, Feynman found the calculation of the scattering cross-section of these processes to be most convenient if they are replaced by certain diagrams, and he formulated certain rules to calculate the diagram so that it gives you the scattering cross-section. So this is the main idea. So anything, so two electrons interacting via, maybe in presence of a potential, and say a k up and k minus k down, these electrons are interacting and they're forming a bound pair and so on. These can be explained, or rather they can be, graphically explained by using Feynman diagrams, and one can easily calculate if you follow those rules. These are given in my earlier course on advanced condensed matter physics, where I actually wrote down those rules and what Feynman used. And if you follow them, then you know that how to calculate the scattering cross sections from these diagrams. So these diagrams are quite important, and they are there in most of condensed matter physics, field theory, high energy physics, everywhere. All these scattering processes are they are represented by diagrams. Aparna, again, explain flux quantization in multiply connected superconductors. So, if you have understood the concept of flux quantization, this is mostly valid in singly connected superconductors. Okay, you say that the magnetic field, if will penetrate the superconductor in the mixed phase of the system, and this quantization of, or there are any amount of flux is this magnetic field multiplied by the area. So if it's there is an area A, say for convenience you can consider it to be a circular area. So the flux will be B into A. Okay, and this B into A is not any number, it's some multiple of this H over 2E. Okay, so this is what is known as flux quantization, mostly applies to the singly connected superconductor. Okay, at least the London equations, etc., they are mostly talking about the simply connected superconductor. Okay. A phonon is, okay, let me go to this. Okay, Rajashri Chakravarti, describe a Fermi sea and energy gap. How is it related to the Cooper pair interaction? Right, this is an important question. This is, okay, so, so you have a completely filled Fermi sphere, which means that at t equal to 0, you have electrons, and these electrons are filling all the way up to the Fermi energy. And you're talking about 3-dimension, and you're talking about a k-square dispersion. K-square means a non-relativistic dispersion, in which case the Fermi surface is like a sphere, because you can go equally or homogeneously in 3 directions, kx, ky, and kz. Now, that is completely filled by electrons. All the states available is completely filled. The question is that now the energy, now there is no space inside, there is no state inside that filled Fermi sphere. All right. So if there are 2 electrons that appear just outside the Fermi sea within a small energy interval given by the h cross omega d being the this Debye frequency or the phonon frequency, then they can form a pair in presence of infinitesimal attraction. Who would give it? It is given by the phonons. It's mediated by the phonons. If you look at my derivation where I actually said that there is an indirect interaction between the electrons mediated by phonons and calculated the scattering cross-section using a second-order perturbation theory, then you'll see that there's a small range over which this interaction can become attractive or negative, or the potential can become negative, and that's how the electrons will form a Cooper pair. Once this Cooper pair is formed, you require a certain amount of energy to break that pair. That is called as the energy gap. Okay, so that is the energy gap that one talks about. Can I go a little up? Yeah. This is done. Feynman diagram is done. Rajashri Chakravarti, I just answered the question. I hope you are comfortable with that. Vaishnavi, once again, phonon is a lattice excitation. Just like photon is a quantum of the electromagnetic radiation, phonon is the quantum of lattice excitation. Okay, so if you think that these ions are there at the lattice locations, and these ions can vibrate about their mean position. Either there could be in plane vibration or there could be out of plane vibration. And these vibrations are, these quantum of vibrations, lattice vibrations, are called as phonons. Okay, so definitely when an electron is actually scanning through the lattice or passing through a lattice, it experiences the existence of phonons, and because of the presence of phonons, these actually form an attractive interaction or a negative potential. Okay, so this negative potential is purely because 2 electrons interact not directly but via a third party called as phonons, which are just the lattice vibration. So if you want to know what phonons are, there is an elastic theory of crystals which you can study, and in which it is just Hooke's law. You have studied this in your first year or first undergraduate level, that what are springs. Springs follow Hooke's law, that if you actually stretch a spring, then the force is proportional to the displacement, and it's actually a recoil, or rather it's a sort of a force that wants to come back. So F is proportional to x, and it's equal to minus kx. So these are like springs. So we actually assume that these ions are held together by a spring, and there are these spring forces. So you can just write down a classical equation of motion for these ions and get these Debye frequencies and get the frequency spectrum of all these phonons. Okay. Chandan Patra, you asked that the K and minus K. Yeah. No. See, this is a very bad, way of looking at things. A bad way means is a wrong way of looking at things. That these electrons, when they form pairs, it's got nothing to do with if they go together, they will break apart. There's nothing like that. Okay. Once they form a bound pair, the binding energy is quite large for them to hold, and there's nothing that can break them apart other than temperature and magnetic field. Okay, so if just without the presence of magnetic field and temperature, thermal effects, they would be pairs all their life. So even if they, travel together with some distance or throughout the length of the superconductors multiple times, nothing is going to happen. They have formed a bound pair and going to stay there. So this binding energy of the pair is large enough for them to be, it's still in milli electron volt, and it's still maybe a few Kelvin. But if you're not talking about temperature, just talking about them, drifting apart, then there's nothing that break them apart. Okay, I hope it's clear now. Okay, this is that is done. Understand the basics of superconductivity. Prasanna Das, things can't be helped. I mean, this is a slightly advanced course. It is, I said, it's a brief course because the duration is only 4 weeks, and but it is quite an advanced course. Superconductivity itself is a very challenging subject, and as you know, that 1908 is when it was discovered, and still people are doing research on that. So what could possibly do a research on, 110 years, 111 years have gone by. And when people are still doing research, there are more to learn. And if had it been simple, then people would have learned it anyway. And in any case, I'm not making this course too advanced, but it has to have mathematics in order for you to understand things. You cannot understand formation of Cooper pairs without doing second order perturbation theory. And if I say that, okay, Cooper pairs are formed, I'm not too sure whether it will satisfy you that, okay, it's okay that Cooper pairs are formed because sir is saying. It doesn't happen that way, right? So I have to give you justification, and which is a justification to myself as well, that I have been able to convince you that yes, there could be attractive interactions under certain conditions, and that's why this superconductivity is possible. And BCS theory is the first and only microscopic theory of superconductivity. And the variational, the way I have done it, there are two ways of doing it, and I have actually chosen the simpler way. Okay, I've chosen the simpler way because I've chosen a variational way. There is another way which is mathematically a little more, strenuous. But people who love mathematics would have been more, happy with that thing, which is through a transformation called as a Bogoliubov-Valatin transformation. So I didn't do it that way. I do it the variational way if you go through my lectures. Yes. Ankush Bhaduri, how is strange metal different than a normal metal? Good question. Strange metal would probably have the Fermi liquid theory. All the properties of Fermi liquid theory may not be valid. Okay, so go through my lectures on the Fermi liquid theory. This was proposed by Landau, and in which he said that these almost non-interacting, the theory was cast in the form of a non-interacting electrons, but it still takes into account electrons, interaction between the electrons in some form. And there are several postulates of this Landau's Fermi liquid theory. I have discussed it to the extent it is doable or understandable by a general audience. But it is much more when you actually do a full course. It could be a full course Fermi liquid theory. So just to answer your question, that strange metals are the metals which do not obey all the characteristics of a normal metal, that is all the characteristics of the Fermi liquid theory. Okay. Ankush Bhaduri, again, dx square minus y square. Achha, so d, this you have to learn a little bit of group theory. So we are talking about the irreducible representation of a square lattice. Why square lattice? Because the copper oxide planes, the copper ions which are in the 3d9 configuration, they are forming a which has a d hole rather. D hole means it's a hole having a d character. D character means the dx square minus y square character. We are so if you look at the symmetry and the the group theory of square lattices, this d x square minus y square is one of the irreducible representations, which happens to be most dominant in the superconductivity of these cuprates. Okay, there are others like Txy, Dyz, Dzx, or the extended S wave as well, but they are not as dominant as this dx square minus y square, which simply means that can I have this board once again? Let me just explain you through an example. So in the S-wave superconductor, we have said that delta or the energy gap has a form which is independent of K. So in standard BCS, which is independent of K. K means momentum. All right. So this is for the S wave, the on-site S wave. The D wave, x square minus y square, has a form where it is like a delta 0 and a cosine kx and a minus cosine ky. So this is called, so there is a K dependence or a momentum dependence of the D wave order parameter, and this is how it is different than the S wave order parameter. So, so this has it has a kind of a dumbbell-like structure. Okay, so it has. So if you look at the Fermi surface, so it's the drawing is very bad. So it's a Fermi surface which has 4 nodal points like this, and this are. So I'm just superposing this D here and drawing it like this. Okay, so this is the filled Fermi C, and the delta superposed on top of that has a form like this. So you have nodal points here. Nodal means here these Cooper pairs can be broken without applying any energy. That is, probably zero magnetic field or zero temperature. They can be broken, and but you need certain amount of energy to break this. So as opposed to the S wave has same energy gap everywhere. Okay, it's the same energy gap everywhere. So you require same energy at all values of K. Wherever this Cooper pair is, you need the same amount of energy for it to break and give rise to a normal state, which is not the case for a D wave. Prabhakar and Aruna, the Cooper pair concept, first electron release energy and the second electron absorb energy, net result is that yes. So what happens is that I mean, basically there is a phonon there, and the phonon has certain momentum q. So one electron actually take that momentum and it so happens that the electron forms a a pair by exchanging through the exchange of that phonon. Let me make it a little more clear that there's an electron which is moving through the ionic lattice, and when the electron sees another electron, that electron is already covered by an ionic cloud, a charged cloud, which is positively charged. So the electron doesn't see the other electron directly, it sees a positive cloud. And because it sees a positive cloud, electron gets attracted and forms a bound pair. Now you could ask the question that why is that that the other electron also doesn't see this electron as a charged cloud or an ionic cloud. That also can happen, but that happens at a much lower scale, time scale. The other electron means the other charged cloud doesn't see this electron as a charged cloud, and why does it see just as an electron? That also happens, but the time scale over which it happens is very large. Okay, so we see what happens the quickest, because that is most likely to happen, or the probability of that to happen is largest. So one electron sees the other electron as as an ionic cloud and gets attracted and forms a pair. That's the way. I mean, that's a hand waving way or a kind of physical way to understand how pairs are formed. Quasi-particle is not QU, but it's QUASI. Okay, anyway, so quasi-particle is a particle which is dressed. Dressed means the mass is renormalized. Okay, so the mass is renormalized due to the interactions. But once the mass is renormalized, it becomes just like a free electron. So the quasi-particles, Cooper pair is a quasi-particle. So quasi-particles do not interact with each other. Okay, the whole idea of Fermi liquid theory is that once you take an interacting electronic system and you apply the Fermi liquid theory, that is, the electrons are interacting with each other in such a way that you can consider these electrons as having renormalized mass or dressed particles. These dressed particles are the quasi-particles. Once they become dressed, they no longer interact. Okay, so this is the meaning of quasi-particles. Semiconductors cannot be converted into superconductors. I think I've mentioned it in some form. That the semiconductors have energy gaps which are of the order of 1 electron volt, maybe a little less than 1 electron volt, maybe 0.7, 0.8 electron volt, whereas these superconductors have energy gaps which are of the order of milli-electron volt, so 3 orders of magnitude lesser, and there is no way that the semiconductor can be converted into superconductors. The other problem is that the superconductor has one state below the gap, one coherent state comprising of many Cooper pairs, coherent Cooper pairs, and they have same energy. Whereas below that semiconducting gap, you have this valence band, which is not a single energy level. Okay, so there's a big difference between the gap that you have in superconductor and the gap that you have in semiconductor, apart from the magnitude. Okay, so this should be kept in mind. Okay, so TJ model and TJU model, I think I have discussed it in the course. That U term is added simply by hand to make you understand that these electrons are interacting with each other. The TJ model is the same model which does not allow double occupancy. So because the electrons are interacting strongly, there can't be 2 electrons at the same side, because that will cost a very large energy gap, or it will cost a lot of energy. So that's why it doesn't happen. So TJU model is really the same as the conventional TJ model, I found it easier for you because the TJ model has to be, if I had to do it in the class, I had to use a projection operator to project out the doubly occupied sites. That would have made the mathematics little more difficult, whereas the TJU model was simpler to handle, at least so I thought. So the physics of TJ model, conventional TJ model with no double occupancy, is same as the TJU model with U being large. Quantum mechanics. Okay, so good quantum mechanics book is by Shankar, R. Shankar, I think Yale University. Very good book. Also, you can see a nice book by Griffiths, the same Griffiths as electrodynamics. He also does it very well on quantum mechanics. I've already explained Fermi C. It's basically just the completely filled electronic states in the Fermi sphere is called as Fermi C. Two-fluid model of superconductivity is there's an old concept saying that it is always there are two models present. One is called as the normal fluid and the other is called a superfluid. So as you raise the temperature, the normal fluid weakens, and the superfluid, if you increase the temperature, the superfluid weakens and the normal fluid gains strength. Whereas if you change or if you reduce temperature, then the normal fluid weakens and the superfluid gains its prominence. And one can think that it's like a two fluids coexisting. This gives rise to the superconducting state, but don't take this very seriously because this is serious. This is only a hand-waving model. It is not a microscopic model. When you come to BCS theory, you'll see that there's nothing like that. Okay, so of course the order parameter gradually goes down. It's a second-order phase transition, but there is nothing like. Well, some of the experiments that we have discussed in the course actually suggest that there are some electrons hanging around and there are some free electrons in the superconducting states, which is causing, the sound transmission or ultrasound transmission and so on. But I guess these are mostly hand-waving arguments, not too rigorous. SP and D wave, they all depend on the symmetry. You have to understand the symmetries of these pairing states. So just like the D wave comes, the S wave, the normal on-site S wave is K independent, momentum independent. The D wave has a dependence which is cosine Kx minus cosine Ky. Whereas the P wave has the dependence which goes as sine Kx or sine Ky. Okay, so this is the difference between P, SP, D. Is superconductivity? Oh, very good question. No. Superconductivity is not possible in photons for the reason that there is no chemical potential well-defined chemical potential for photon. So mu, which is defined as del F del N, is so F doesn't, the free energy doesn't depend upon the number of particles for photons, and that is one reason that if you can't have a Fermi surface just as you had in an electronic system, you can't have such a thing for a photon, so they don't condense, and you can't have it in fiber optics. Specific heat. Yes, can I have the board? So this is specific heat C, and this is T. So it grows like exponential, and at T equal to Tc it drops, and then this is like your normal electronic specific heat. So this is the Tc. So at very low temperature, it has an exponential, this thing I've also explained it in class. It has an exponential dependence, then it drops. So there is a certain amount of drop. And this is the hallmark of a second order phase transition. And then of course, this is no, this goes as linear in T, which is in normal metals at low temperature. This is the dependence, specifically it as a function of temperature. This is Ankush Bhadri. This is another good question. That what is the difference between a gap in the antiferromagnetic insulator and a superconducting? You mean to say a superconducting region in temperature versus doping plot? Oh, the antiferromagnetic insulator. You mean to say that what quantity is that? I mean, antiferromagnetic insulator doesn't have a. If you say a ferromagnetic thing, then I can agree. If ferromagnetic, the magnetization versus temperature, and this superconducting order parameter versus temperature, they are exactly same. Okay, but antiferromagnetic insulator, this gap, it of course as a function of U, it goes up or down. As you increase U, this gap becomes larger and so on. But that temperature, because this antiferromagnetic insulator, the gap is about 5 or 6 electron volt. That is too large for us to talk about. And 6 electron volt is like what, about 80,000 Kelvin. 80,000 Kelvin is not a temperature that you want to kill anyway by using thermal effects. So ferromagnetic gap versus temperature, superconducting order parameter versus temperature, dependence is exactly the same, if that is what you're asking. All right. Ultrasonic attenuation, I was saying that, if you send ultrasound through a superconducting material, then it will, either it will pass the sound and you can collect the transmitted sound, or you may not be able to collect the transmitted sound because there's a decay of sound in presence of normal electrons. So as the electrons are present in superconductors, the ultrasound will decay. Okay, and if it's perfectly in the superconducting state, then the ultrasound will pass with the same, nearly the same intensity. Okay, so as you are getting into a state which is normal state, that is, if you're increasing temperature, say for example, you are having more and more normal electrons appearing into your system, and these normal electrons will absorb the sound. That's just electron phonon interaction, and then you get the sound intensity to be less. This is how so at a point when you don't get any ultrasound transmitted through the system, then you know that it's no longer a superconductor, a normal metal as setting with all electrons, free electrons being present. Okay, yeah. Renormalization group in superconductor is I have to think about it, because renormalization group, the way it works is the following. You decimate a system. So you take away degrees of freedom from a system, and finally the system reaches a point which is called as a fixed point, and that even after further decimation, the system doesn't evolve. So that talks about a phase transition. Okay, so this is very well understood in the concept of magnetic phase transitions. But whether people have also used it, I'm sure there are studies, but often I cannot recollect. I have to see whether renormalization group studies have have been done in superconductivity. Question papers will be mostly from the the assignments. So please do those assignments carefully. One Dr. Viraswamy Kiaragrani is asking that how do I let my undergraduate student understand about Meissner effect. So Meissner effect is important for understanding superconductivity. It's the most important thing rather. It tells that the magnetic field is strongly repelled from the superconductor. So if you try to put a superconductor in a magnetic field, the flux lines will all go around that specimen, and the density of flux lines will be largest in the immediate vicinity of the superconductor. And this is the the principle that is used by these magnetic levitating trains. All right. So you can tell that it's the expulsion of the magnetic field that is called as Meissner effect. So no magnetic field is allowed to enter. And why is that? That is because if magnetic field is allowed to enter, this would cause current, normal current to flow through the sample. But superconductors do not allow passage of normal current. So that's why the electrons cannot. So free electrons cannot survive in a superconductor. They are all thrown out, or they are not there. They have all been as Cooper pairs are formed. Okay, so that's the reason. There are no more questions. I mean, there's one question. dB/dt is the change in magnetic field with temperature, and you can sort of the same. If there is a relation for dB/dt, the same relation also occurs for B. So if you see that equation that we have written, it's del square B, and which is related to or del square dB/dt is related to dB/dt. We have written that by doing an integral over time as del square B equal to some lambda L square into B, and then we have solved that equation for the special variation of the magnetic field. So thank you very much. I hope I've been able to answer most of the questions, and all the best for your final exam and for the course that's ahead of you. Thank you.